Hello, hi everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem, break the tree. And this is one of the beautiful problems which uses the concept of binary search, and it also involves trees. So let's see how we can apply the concept of binary search to these kind of problems as well. So in this problem we're given a tree. A tree is basically an undirected connected graph which has no cycles. So we're given a tree with n nodes and another parameter k. Each node in the tree has a positive weight, okay, and which is represented by the array w. This represents the weights of the corresponding nodes. Now notice here, the weight is not assigned to the edges, but it is assigned to the nodes of the trees. Each node holds a particular value which we call it as the weight of the node. The tree needs to be partitioned into at most k subtrees. So we're given some tree which has n nodes. We can partition the tree into at most k subtrees. For that we have to remove at most k minus 1 edges, okay, such that what do we want to do by partitioning the tree into multiple subtrees? So let's say we have a tree which has n nodes. We divide the tree into some number of subtrees by removing some edges from the tree. Now we have different components of the tree, connected components separated from each other. Each component holds a weight which is equal to the sum of the weights of the nodes which that component has. Now out of all those weights we're gonna pick the maximum weight, and what I want to do is to find out such a partition of the tree such that the maximum weight which I have got out of all those components is minimum, is as small as possible. That's what I want to accomplish in this problem. And we just want to return the smallest value of the maximum subtree weight that can be removed, that can be obtained by removing at most k minus 1 edges, okay. Now at most k minus 1 edges, we may require lesser number of edges for removal so as to get the minimum value of the maximum subtree weight. Fine. So again we have to minimize something such that this again the same pattern. So here we know that we have to minimize. Okay, so that's what we want to do, minimize the maximum weight such that we can remove k minus 1 maximum number of edges, okay, at most k minus 1 edges. So let's better understand the problem statement using an example. You can see that the number of nodes in any typical tree may go up to 20,000, while the number of partitions will lie between 1 and n, and the weight of any node may go up to 10 raised to the power 9. So let's keep this in mind, and let's understand the problem statement using an example. So let's take this example. We have a tree of, let's say we have a tree of n as 3, that is 3 nodes, and we want to partition it into at most 2 subtrees, okay, and the weight of each component, okay, so this is the weight array, this is the weight array, this is n, the number of nodes, this is k, the number of subtrees into which we can partition it into, and this is basically the tree which we have. So let's draw the corresponding tree, okay. So this is the typical tree which we are given in this first test case, and let's write the corresponding weights of the, so let's write the weights of these nodes. The first node has a weight of 5, the second node has a weight of 10, the third node has a weight of 2, okay. Now let's see what's the answer here. What would be the, we can divide this tree into at most 2 subtrees. So to divide it into two subtrees, we can remove at most one edge. Okay. Now let's see the sum of the weights that we have. 5 plus 10 plus 2, that is going to give me 17. Now since I can remove at most one edge, can I minimize the maximum weight? The maximum weight is 17 because we have just one component and its weight is 17. Can I get two components such that this maximum weight is minimized? So let's try to remove this edge. So if I remove this edge, then the components would be like this. I would have a component containing only node number 1. I would have a component containing node number 2 and node number 3. Okay, these will be the two components if I remove this edge. Now, what is the weight of this component? It is 5. What is the weight of this component? It would be 10 plus 2, that is 12. And the maximum weight of all these components is 12. So this is one of the cases in which I remove this edge. Let's take another case. I remove this edge. Then I would have components like a component with node number 1 and node number 2 and a component containing node number 3 only. So this component has a weight of 10 plus 5, that is 15. This component has a weight of 2 only. The maximum weight in this case is 15. Okay, and we can remove only one edge at most. So which one is the better answer? Is it 15, 12 or 17? Obviously 12, because I want to minimize the maximum weight subtree as small as possible. So it is 12. So this partition is the most optimal one. So the most optimal way to make the maximum subtree weight to be minimum is to remove this edge, the edge between node number 1 and node number 2. That is going to give me answer as 12. So answer would be 12 here. Okay, so that's one of the test cases of this problem. Let's see how we can solve this problem. Obviously, okay, so we can see, obviously we can see that we want to minimize something. We want to partition the tree into multiple subtrees by removing some edges, and we also limited to the number of edges we can remove, and we want to maximize the maximum, we want to minimize the maximum weight that we obtain out of all those components. So again, a binary search problem. We got to binary search on something, but what is the variable on which I want to binary search? Obviously we have to perform binary search over the answer. What is the answer? The answer is the maximum weight which we can achieve. Okay, that's the answer. So let's take an example and understand it better. So we have this tree. It has 6 nodes. N is 6, and the maximum number of subtrees into which I can partition it is 3. I can partition it into maximum 3 subtrees. Okay, that means I can remove at most 2 edges, at most 2 edges, and I want to minimize the maximum weight which I can achieve by partitioning it into multiple components. So the answer would simply be that minimum, the answer would simply be that minimum subtree weight that we can achieve. Okay, let's call it x. Let's call x to be the answer. What is x? It is the minimum subtree weight which I can obtain such that I can remove 2 edges. Since this is the minimum, I would be able to achieve x plus 1 as well. I would be able to achieve x plus 2 as well, and so on. How much I can achieve as the maximum weight if I do not partition it into any components. I just take the weight of the entire tree. That would be 2 plus 4, 6 plus 6 plus 6, 18 plus 8, 26 plus 5, 31. So it would be 31 in this case. Or in general case, I would say it's the sum of the weights array. Sum of the elements in the weights array. That's my maximum or the right extreme or the right bound, upper bound we can say. While since x is the minimum one, x is the minimum weight which I can obtain, I won't be able to obtain x minus 1 as the weight. I won't be able to obtain x minus 2 as the minimum weight, and so on. In the same fashion, what would be the left extreme? What is the minimum weight subtree that I can have? Simply I can't go lesser than the maximum weight node that we have in the tree, that is 8. Even if we partition this tree into single nodes, so partition this tree of 6 nodes into 6 different components, then the maximum weight that we can have would be the maximum of all the weights that we have from the nodes, and that would be this one in this case. So the left extreme would be max of the weights array, max of the weights array. That is the left extreme. We can't have a weight in any possible subtree which is less than this weight. Okay, because the worst we can do is to divide the tree into single nodes. Okay, and in that case that would be the weight or the maximum weight or minimum maximum weight which we can achieve. So this is what I want to find. I want to find this value. Okay, the minimum weight which I can obtain by removing k minus 1 edges, that is 2 edges. So since by removing 2 edges I won't be able to achieve these weights, I have to remove more edges, because let's say I want to achieve this one, that is max of the weights of all the nodes. For that I have to remove every single edge of the tree. I have to remove every single edge of the tree. In that case I will obtain this value. Okay, same goes for these values. I have to remove more than k minus 1 edges. This is the first value where I will remove at most k minus 1 edges, and I will get x as the minimum subtree weight. So these are, let's call it bad weights. These are, let's call them good weights. Okay, now I want to obtain this value. This is simply nothing but first true. What? First true. And the implementation of this function, calculating the first true in a monotonic search space, we implemented a function that is discussed in the very first video. So you can watch that video if you do not get what is this first true. So we want to find this value x. We have the left extreme, we have the right extreme, or the search space in general. We want to binary search over this search space and we want to find this x. That's all. Now simple, we have the search space. Now find the middle element. Find the middle element of this search space. Check if it lies on the bad side or it lies on the good side. If it lies on the bad side, let's say it lies here, then that means we are on the wrong side. We will never find our first x on the left of this point. Okay, so I reinitialize the search space to this one, that would be mid plus 1. too high. Okay, otherwise if the mid lies on this side, let's say mid is here, that means I'm on the wrong side. I will never find, that means I'm on the right side, but I will never find the minimum x on this side, on the right side. So in this case the search space is reduced to low to mid minus 1, where mid can be my potential answer. Okay, so in this fashion I will keep reducing the search space until the search space contains exactly one element, and that element has to be this x. Fine. Now let's see how we can basically find the predicate function, or how we can check if the guessed mid lies on the good side or it lies on the bad side. Let's figure that out. Okay, so let's understand, let's find the definition of the is valid or boolean function from this given tree. So this is the tree which has 6 nodes, and so n is 6, and we can divide this tree, we can partition this tree into at most k subtrees, where k is 3 in this case. Hence we can remove at most 2 edges. We can remove 2 edges at max. So how we can do that? What is the strategy to figure out, let's let's say the guessed mid is this is the guessed mid. That means we can't exceed the weight of any subtree than this mid. We can't exceed this mid. Okay, while calculating the weight of any subtree, we have to divide this tree into subtrees in such a way that the weight of the subtrees will not exceed this mid. How can I do that? Let's see. So let's start from this node, that is the root node, the node number 1. We move down, we move to the children of this node. We have children as 2, 3 and 4. We have 3 children. Now what I would do is, there are 3 edges which are connecting these 3 children. I will check the possibility of removing any of these edges. So initially the weight for node number 1 is 2. Then I will move to the very first children which has the smallest weight, that is node number 2. Fine, so we will add this children, because we can see that if I add this child, now what I can do is, I have 3 childs for this node 2, and I want to figure out if there is a chance, if there is a possibility that I have to remove one of these edges or more of these edges. For that, if I want to keep this edge connected, that means I have to keep this component connected. If I want to keep this node connected, that is node number 3, then I have to keep this component connected. In the same fashion, if I want to keep this edge to be connected, then I want this component to be connected. For that, let's say this component has some weight x, this component has some weight y, while this component has some weight z. This is not the weight of the sum of these nodes. No. This is the weight of the component which I want to connect with this node 1. Okay, I just don't know whether this node will be removed or this node will be removed. I have no idea for that. I just know that okay, I want to keep this node number 2 to be connected with this node number 1. Okay, that's what I want. And for that, what is the maximum weight which I can get from this node? That's what I'm asking while standing on node number 1. And the answer is x. X is the maximum weight which I can ask from node number 2, so that this node, so that the weight does not exceed this mid, and I can keep this edge to be connected. Okay, so out of these x, y and z, I would first choose the weight, which is minimum. Okay, so I would choose 2 plus, let's say, x is minimum. Then I have to check if this 2 plus x exceeds this mid or not. If this exceeds, then that means I have to remove this edge. I have to remove this edge. If this does not exceed, then I can check for the next component, let's say y. So if I sort these weights, then they are like this. I'm assuming to be like this. I'm assuming them to be like this, in this fashion. X is smallest, y is greater than x, z is greater than y. So then the second will be y. Can I include the component which has a node number 3? I don't have to worry about the children of node number 3. I just want to keep my node number 3 connected with node number 1. For that, I have to include a weight of y in this component. The component containing 1, 2 and 3. Fine. Now, if this exceeds the mid, then that means I can keep 1, 2 in this component, but I can't keep node number 3 and node number 4 in this component. Why? Because their weights, if I add any of them, they're gonna exceed this upper limit mid. So I can't include node number 3 and node number 4. So I have to remove this edge in that case. So if this does not exceed this mid, then that means I can also include 3 in the component. So I move to the next value, that is z. Now again I will check if this z, which is the maximum weight of the component which has this node number 4. Okay, this z obviously must not exceed mid. All of these x, y, z must not exceed mid. Now I will check if this entire value exceeds the mid or not. If it does not exceed, that means I can include 4 as well in the component containing 1, 2 and 3. So the component will have 1, 2, 3, 4 at least. That's what I'm ensuring. I don't have any idea about these nodes, the nodes below this node 2, 3 and 4. Okay, but I know that this is not exceeding the mid. If it is not exceeding, then I will include that node. Otherwise I have to remove that component. I have to put a cut here. I have to remove this edge. So that's the strategy. Standing at any node, I will have to check these things. I will do the same while I move to node number 2. Okay, so I come to node number 2. I find the subtree weights, the weight for this subtree, the weight for this subtree. Okay, and that is the maximum weight which I can get such that it does not exceed this mid for each subtree, this and this. Okay, let's call them to be, and then let's say they are a and b, small a, small b. Then I will sort these weights, and I will keep adding the weights in ascending order into the weight of this node 2. And I will check if while adding those weights, if I exceed the value mid or not. If I exceed the value, then I got to remove that edge. Otherwise I don't have to remove that edge. That's the strategy, and this is a recursive step. I have to do this for all the nodes of the tree. So first I will do it for 1, and while doing it for 1, I will recursively call the same function for node number 2. So it will do, we'll start the process for node number 2. This will recursively start the process for node number 5 and node number 6. So every node is going to return its answer, and from that answer the parent node will evaluate the answer for its subtree, whether we can include the particular children into the current subtree or not. So I hope you're getting where we are going. Let's take a better look on this solution by using an example. Okay, so let's see, we have a, so for doing this, since I want to traverse every single node, I want to perform the process for every single node, I will use depth first search strategy. I will use depth first search strategy to do so. So initially I will start my DFS from node number 1, and let's say its parent is node number 0, which is a hypothetical parent. We don't have node number 0 here. So this we're passing this parent just because we don't want to revisit the node number 2, node number 1. So I have visited node number 1, and the weight of this node is 2. Okay, the weight of this node is 2. Now I will traverse its child nodes, node number 4, node number 6, node number 3, and node number 2, 3, and 4. So I will call this function depth first search. So first I call this for this one, then I will call this function for node number 4. So this is recursively calling itself for node number 4, DFS 2, and its parent is 1, so that we don't revisit node number 1 again. Fine, its weight is going to be 4. The weight of this node is 4. Then I will recursively call this function for its children, that would be 5. So let's call the DFS function for node number 5, and the parent, that is 2. Okay, now I am over here, so I'm gonna have the weight as 5. Okay, so this has no children, this has no children. So what I'm going to do is, since it has no children, the only weight that I can obtain here would be 5. So I will check if this 5 exceeds, this 5 is will never exceed, does this 5 exceed mid or not? It is not. So this component will return 5. So it is going to return me 5. So this will return 5. Now I come back to this point. I come back to this point. And here, since I have traversed this node, so I have traversed this node, node number 5, I will traverse node number 6 now. That is this one. Again, this has no children, so that this is the base case, so I will return this 8 right from here. 8 is not exceeding this mid. 8 is not exceeding this mid. Let's say the mid guessed, the mid that we have guessed is 15. Okay, now we will return 8 from here. We will return 8 from here. So we have 5 from this side, we have 8 from this side, and we have 4 as the weight of the node on which I am standing. So I am at this function call. The call stack contains, the top of the call stack contains this function call. This is out of the call stack. Okay, now here I have 3 weights, I have 2 weights, so this is not 5, this is 8. I have 5 and I have 8. 5 represents the weight of the left component or this component, while 8 represents the maximum weight of this component. Now here, standing on node number 2, I will check if I can include any of these components. So I will start from the component which has the least weight, that is this one, and I will pick up this weight, and I will check if 4 plus 5 exceeds the mid or not. No, it doesn't exceed. It doesn't exceed, that means I can include this component into the current component which contains node number 2. So that means 5 is included into 2. 5 is included into 2. So the component is this now. I have this component which has 2 and 5 as a unity. Then I will move to this weight. I will check if 4 plus 5 plus 8 exceeds the mid or not. 9 plus 8 is going to give me 17. 17 is obviously exceeding this 15. That means this is the upper limit. I can't have a subtree which has a weight more than 15, but we are getting a subtree which has a weight of 17 here. That means we can't include this weight. We can't include the subtree which contains this weight. So this can't be included. If this can't be included, then I have to remove this edge. I have to remove this edge. So I make a cut here. I remove this edge. Fine. And this, we have this component as connected, and it has a weight of 9. We have made one partition. K becomes 1 now because I could remove 2 edges. Now I can remove only one edge. Okay, now from this node number 2, I come back to node number 1. I come back to this function call. So this is removed from the call stack. This was also removed. Now I am here at DFS10. From this point, I will traverse this node, that is node number 3. So DFS will be called for 3 while passing in the parent, that is 1. So here from this node, I'm going to return 6. 6 is not exceeding 15. So I don't have to make a cut here. I will just return the 6 from here. So I'm getting 9 from here, from this component. I'm getting 6 from this component. I'm standing on node number 2, on node number 1 here. I'm standing here. Then I traverse this third component, and since this function call is out of the call stack, then I will call this function DFS for node number 4 while passing in the parent, that is 1. This is also not exceeding this 15, so I will return this 6 right from here. So I will get a 6 here. So I'm getting 9, 6, 6 from 3 components of this node 1. 6, 6, 9. I will keep them in a sorted order. Why? Because obviously the least the value, the lesser is the chance to make a cut, so that I can involve more and more subtrees into the current subtree. So standing on node number 1, I want to include more and more child nodes. For that, I have to pick up those nodes first, those childs first, those children first, which has least weight. Hence, that's why I'm sorting these weights. I'm receiving 3 weights, 9, 6, 6. I will sort them, and then I will try to include every single one of them. So let's first include this one. Let's first include this 6. So the weight of this node on which I am standing is 2, while the weight of this subtree which we are traversing is 6. Now I will ask whether this 2 plus 6, that is 8, exceeds the mid. No, it doesn't. Okay, then this is included. Let's say this is included in this subtree. Then move to the next subtree, which has a weight of 6. Let's try to include it. Can I include it? 6 plus 6 plus 2 would give me 14. 14 does not exceed mid. Yes, I can include this as well. So I have included 4, I have included 3. Okay, yes, I can include it. Then I will move to the next one, which is 9. Can I include this 9? Let's see. This is going to give me 14 plus 9, that is 23, which is exceeding this mid. So this is not allowed. I have to exclude this component. I have to make a cut here. I can't include this weight, so I have to make a cut over here. Fine. That means this can't be included. So we have made our 2 cuts. We can't make any other cut now. And the weights that we have would be, what are the weights? The weight would be 9 for this component. So let's first check the partition that we have done. We have traversed every single node of this tree, node 1, 2, 3, 4, 5, 6, and we have made a certain partition. We have made 2 cuts, we have made 2 partitions, 2 edges we have removed. The first edge was an edge between 2 and 6, the second edge was an edge between 1 and 2. Now let's see the partitioned. Okay, so these are the components that we have achieved. This component has a weight of 2 plus 6 plus 6, that is 14. This component has a weight of 8. This component has a weight of 5 plus 4, that is 9. Now any of these weights is not exceeding this mid 15. It's not exceeding this mid 15. They are 9, 8 and 14. So for this guessed mid, which was 15, I'm going to return true. Why? because what is the maximum weight? It is 14. It is not exceeding this 15. Hence, 15 is the 15 lies on the good side. 15 lies on the good side here. 15 lies somewhere over here. That's why I'm returning true from this partition. So in this fashion, I will partition my tree according to the given mid that we have guessed. Fine. And eventually I will arrive at my first minimum mid where I can partition the subtree such that the maximum weight is not exceeding the given mid. Okay. So let's see the implementation of the idea explained here. So before you watch my implementation, if you have understood the idea, the solution till this point, then try to implement the solution by yourself. That is going to increase your implementation skills, your speed a lot. After you implement your solution yourself, you can watch my implementation. So let's see that. So this is the implementation where this is the graph. Okay, this will basically store the given tree. This is the weights array. We're going to store the weights in this array. This array is going to store the weight of the subtree for every node. Okay, so this has the size same as the number of nodes, and for every node it will store the weight of the subtree for that particular node. Okay, so this weight here, while standing on node number 2, I had the weight 4 plus 5, 9. So this 9 will be stored in this TOT array. Okay, so this is the max subtree weight function, which takes in the number of nodes, the maximum number of subtrees which I can partition the given tree into, resize the graph and store the given graph into this, and this is the node, resize this weights array and this TOT array, and store the corresponding values in them. That is the graph, the adjacency list, the weights array, and initialize this to 0. Now take two variables, which is min, okay, and which will represent the minimum value subtree we can achieve, while this is the variable mx, which is the maximum value subtree which I can achieve. Obviously this minimum will store the maximum value of the weights that we can have, because in the worst case we can partition the given tree into the subtrees containing each one node. In that case, the maximum weight node will be the minimum value which I can achieve, while on the other extreme, the maximum weight subtree will be the entire tree itself when we do not remove any edge. So this will simply store the sum of all the weights of the nodes. So iterate over all the nodes, find the maximum weight, store it into mid, store it into mn, while find the sum of all the weights, store it into max. Then initialize a variable answer, which is gonna store that first true value. Then initialize two variables, low and high, which represents the search space. Low will be initialized to mn, high will be initialized to mx. These are the left and right extremes for the given search space. Again, perform the usual binary search, low is less than equals to high, find the middle element. This C is declared globally. This is basically used to count the number of subtrees that we have partitioned the given tree into. So that's why I am initializing it to be 0 here. Then I will call this function DFS. Now this mid I can pass into this DFS, but let's take this mid to be a global variable. That means this mid is accessible into this depth first search function. Also C is also accessible into this depth first search function because they are global variables. Now here this depth first search function will simply check if we can remove at most k minus 1 edges, which is counted by this variable C, and the maximum subtree weight is not exceeding this mid. If it is the case, then that means C is always less than equals to k minus 1. The number of edges that we have removed is always less than equals to the number of edges that I can remove. If it is the case, then this mid lies on the good side, and hence reinitialize the range to low to mid minus 1, while the mid on which I am standing is also can be the valid answer because it lies on the good side. So I store this mid into the answer variable. Otherwise, this mid lies on the bad side. So reinitialize the range to the mid plus 1 to high. Okay. Finally, at the end, return this variable low. Okay, because this is going to store that first true value. Now let's see the implementation of depth first search function, which is the most important part of this video lecture. Let's see. Okay, so this is the DFS function which takes in this node on which I am standing, the parent node, which simply helps us to not visit the parent node again. This total array which we declared initially, for this node it will simply store initially the weight of that node that we have. We don't know at this point how much children nodes we have to include. So this array, let's take an array ARR. This array is going to store the weights of the subtrees for this node. So for all of the children, this array is going to store their weights in the sorted order. So I will iterate over all the childs here. I will check if the current child is not the parent. Then for every child, I will recursively call this depth first search function again here. Okay, and since this depth first search function basically returns the maximum weight for the subtree which I can have rooted at this node, I'm gonna push that weight into this array. Okay, finally, when I have traversed all the childrens, when I have found the weights of all the childrens, the optimal weights, then I will sort the array ARR into ascending order, and then I will iterate over that array and I will try to include the components starting from the component which has the least weight. Okay, so V represents the particular component, the weight of the particular component. If I can include that component, that I will check by simply adding the weight of the current component on which I am standing to the weight of the node that I have. If this basically exceeds the mid, here it is exceeding the mid, then I have to make a cut here. Here I have to remove that edge, and that's what I'm counting here. C is representing the number of edges that we have removed. So here I have to remove the edge because I can't include this child into the current subtree because it's exceeding the mid. So make a cut here. Otherwise, include this child into the current subtree. And since I'm including this child, so let's say I'm standing on node number 1, there is some children which is rooted at node number 2. So some children rooted at node number 2. It has some weight x. This has some weight y. So y plus x. If this is not exceeding the mid, it is always less than equals to the mid, which is the upper limit for the maximum weight which we can have for any component, then definitely I can attach this component to this node. So the final component would be like this, 1, 2, something like this here, and its weight is not exceeding this mid, so it's a valid component. So I am including this component here. Fine. And at the end, I will return the weight which this connected component can have. That is y plus x, which I have stored for at this point, at this location. Okay, that is at the root of that tree, at the root of that subtree, and I will return that right from here. Fine. So you're getting what we are doing in this implementation. If you have a basically, this is just a little tweak in the depth first search strategy. So if you have if you understand how depth first search works, you will be able to understand this implementation quickly. Otherwise, you will have a trouble. So in this fashion, I will calculate my first true value, which I am returning right from here. And now I hope you got the implementation. Let's jump to the time and space complexity. So we can see that we are performing depth first search. Okay, so what is the range? So as we know, we are performing binary search. The binary search is performed over the range that is the maximum element in the weights array up until the sum of all the elements in the weights array. That's what this sum is representing, the sum of elements of all the weights in the given weights array. And that is basically the range of the binary search. So log of sum of w multiplied by the complexity of the depth first search, because for every iteration of the binary search I'm performing a depth first search, which is going to take the linear time complexity. So n log sum of w will be the final time complexity, while the space complexity will be big of n, because I'm using a lot of auxiliary arrays to store different variables. For instance, I'm using this tot variable. For instance, I'm using this tot array. I'm using this array here again one more auxiliary array to store these weights. So in this, so that's why the time complexity would be big, that's why the space complexity would be big of n. Fine, so let's jump to the code implementation part. So let's take this function, let's call it minimize minimum weight subtree, which takes in this weights array graph and the number of nodes that we have and the variable k. Okay, now let's declare a vector, let's call it tot, resize this tot to the number of nodes that we have, then initialize two variables min and max, iterate over all the elements of the given weights array, extract the maximum element in this variable, find the sum of all the elements into this mx variable. This is going to represent my lower boundary and the upper boundary. Initialize the variable answer and variable low, which is basically, let's call it long. Let's call this as long. This one also as long. Okay, so for that I have to create another function, long max, long a, long b. So I have to return if a is greater than b. If it is the case, return a, otherwise return b. So this is going to return the max of the values that we have passed. So low, initialize it to mn, high, initialize it to mx. Perform the usual binary search, find the middle element, long mid, high minus mid divided by high minus low divided by 2. Okay, we have to declare a variable c as well. So declare a variable c as well, which is gonna represent the number of components that the number of edges that we have removed. So call this function depth first search for this node that we have. The root of the node is 1, so I'm starting the depth first search from the root node, and the parent would be 0. Pass in the graph as well, the weights array, this tot array, as well as this c and k as well. Finally, this is gonna do its job, and it is going to check if we have the number of edges that we have removed are less than equals to k minus 1. If it is the case, then this can be my potential answer because it lies on the good side. And reinitialize the range to left half, so mid minus 1. Otherwise, reinitialize the range to this one. At the end of the return low. Okay, so here we can see that, let's just see the function here, which is node, and then we have this parent, then we have this graph, then we have this array dot, then we have this variable c. So we don't have to pass k here, just pass c. We don't require k at this point. So here let's see. So again, for this dot, for this current node, just store the weight of that node here. Store the weight. Okay. Then declare an array which will store the weights of the subtrees in the sorted order. Iterate over the given graph. Check if I can include this component or not. Iterate over this graph, and if this is not the parent, I'm iterating over the child node, then recursively call this function dfs for the child and push the result into this array. Dfs for this node it, the parent is this node, this is the graph which I'm passing, dot array and c. So we'll have this array prepared, sort this array in the ascending order, then iterate over this array and check if this current weight can be included or not. If it can be included, if it exceeds this mid that we have guessed. Okay, we forgot to pass this mid. This is a local variable, so I have to pass this mid here as well. So I have to pass this mid here as well. Okay, so if it exceeds this mid, then definitely I can't include this component into the current component rooted at this node. So remove this edge, otherwise include it. Fine, that's all. At the end, return this total weight that I can get for this node. While this is going to count the number of edges that we have removed, while maintaining the maximum weight, like less than equals to mid. That's what this function is doing. So after its job is done, we have simply checking if the components that we have broken the tree into is less than equals to k. If they are, then that mid that we have guessed, the weight that we have guessed, lies on the good side, otherwise it lies on the bad side. So in this fashion this function is working. Let's see this is the implementation in C++. Let's see the implementation in other languages. Okay, so this is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel. And here I'm marking the end of this series. If I find any interesting problem of binary search, I would definitely try to upload the problem in this playlist. But I think that it's enough if you can solve problems of these categories which I have solved. Then if you encounter any problem of binary search in the future, then it is more likely that you will be able to solve this problem after you have watched the playlist at till this point. Okay, so that's all. I hope to see you in my next playlist or in my next video.